Moving into Chapter 3, we are focusing our time and effort in displaying and describing categorical data. So this is going to be the main focus for this chapter, and then the rest of the unit is going to focus on quantitative data. So it may seem basic, and you guys may think this is a little bit too simple, but do take the time to get good at dealing with categorical data now. So when we deal with it later on in second semester, you're not struggling with contingency or frequency tables. So again, I put up the homework for you here. It will also be on Schoology. And let's get started with a little bit of your turn. So listen to this. It should sound familiar to you guys, and then we'll get back right quick.
The wheels on the bus go round and round, round and round, round and round. The wheels on the bus go round and round, all through town.
Now you may be saying to yourself, Mr. Swenson, why are you talking or showing us the wheels on the bus go round and round? And it's simply because when you hear this phrase over and over again, you know what is going to go on and what the verses are. So I say this and use that as a way of introducing the 3 rules of data analysis. And there are 3 rules. They're simple to remember. I will say, number 1, draw a picture. A picture is an illustration of the data and can show any trends, patterns, or unusual characteristics of the collection that is not obvious in a simple list of data. Option 2 is to draw a picture. Patterns in the data can be seen in a visual representation of the data, and you may see things that you would otherwise miss. And thing 3 is to draw a picture. I hope I'm making my point crystal clear here. A picture is worth 1,000 words. Not sure I agree with that, but a picture allows you to more easily explain your words. And that is the trick with statistics. We are giving images and context to the data and explaining what is going on. So 3 rules of data analysis is to 1, draw a picture, 2, draw a picture, and 3, draw a picture. Now, with that being said, if we are dealing with frequency tables usually show categorical data of different types and their counts next to them. So we can organize the data by counting the number of data values of some category of interest. So we organize the counts into a frequency table, which simply records the category names and the total frequency within each category. Hence, counts and different type. So first class, second class, third class, and the crew. And these are the counts of those, in this case, people. I want you to think maybe what would talk about first class or second class or third or even the crew. Second way of looking through a frequency table is a relative frequency table. It's virtually the same thing, but gives the percentages or proportion of each category in place of the absolute count or category. Oftentimes people use relative frequency tables if they're dealing with pie charts. Because pie charts are dealing with the percent of a whole, you do lose some context with relative frequency tables because you don't know the total amount that you're dealing with. You're just dealing with percentages. Other times dealing with percentages is quite useful, so we should be able to work between these 2 types of representations. With frequency tables, both types of tables show how cases are distributed across categories. That's why we call this categorical data and not qualitative data. Do not use that word, please. Frequency tables illustrate the distribution of a categorical variable as the table names the possible categories and indicates how frequently each category occurs. So if we go back to our frequency table and we think first class, second class, third class, and crew, if I told you, is this a good way to show the Titanic data with this display? I want you to think about this, and if I can, I'm going to have the video pause and ask you, is there anything wrong with this display of data in terms of this picture? Now that you've put your own thoughts into this, I want to say that this, albeit creative, is an awful way of representing the data. What does a ship mean? Is first class, where do you measure to? The big side, the small side? Are you saying that we have 300 or so in first class, and in third class there is about six? What is this number here? How do you tell what this represents for the third class? Additionally, how many of these little ships can fit into the crew or third class? This is a bad representation of the data. So don't try to be cute. Don't try to be clever. This is a violation in statistics of what we call the area principle. So the ship display makes it look like most of the people on the Titanic were crew members, with a few passengers along for the ride. When looking at each ship, we react to the area taken up by the ship instead of the length of the ship. The length is the only valid characteristic when we are looking at this display of data. The ship display violates this area principle. And so we say the area occupied by a part of the graph should match the magnitude of the value it represents. As I said before, do not get creative. Do not be clever or cute or fancy. Just show me the data. Stick with a bar chart. It's simple. It's easy. Your calculator will put these out real quick. And I will show you in class how to make this chart into both a relative bar chart and a bar chart, frequency bar chart. So a bar chart displays the distribution of a categorical variable, showing counts for each category next to each other for easy comparison. That's what we want. Thus, a much better display for the ship data looks like what we have pictured here. This bar chart stays true to the area principle. I also want you to note there are gaps between these bars. It is not continuous, and that is the point of categorical data. They're not interrelated. This is not on a continuum, so we keep things separated. With bar charts, you could also represent this with a relative frequency bar chart, and that is the display of the relative proportion of counts for each category. If you think relative, I want you to think percentages. If we're just talking about regular bar charts, we're talking about the frequency or the counts. So simply replace absolute counts with percentages in the data for relative bar chart. The relative frequency bar chart also stays true to the area principle if we showcase this picture here. And the only difference between a frequency bar chart and a relative frequency bar chart is the vertical axis. So we're looking at the vertical axis. Also note that these axes are always labeled. Here we have percentages, and if we go back here, we show the frequency in terms of counts. So these are the people in each one of those bins. Another way of displaying categorical data is with a pie chart. So if you're interested in illustrating the relative size of parts of a whole, a pie chart might be your best choice. And with pie charts, they show all of the categories as a section of a circle because it's a pie chart. So pie charts divide the circle into sections whose size is a proportional fraction of the whole for each category. So what you should do if you're calculating the area that's going to be represented by the crew, we take the number in the crew divided by the total number of passengers, and we'll multiply by 360. If you really want to be fancy, you could also do 2 pi. We're not fancy in this class, so we're going to stick with degrees, and you get about 145 degrees. The angles that are taken up by the proportions should match what you expect. Next up, a contingency table, or a two-way table. A contingency table allows us to look at two categorical variables together, and it's important. We will be referring to contingency tables several times later in this course, so remember this topic. It may seem simple right now, but it's going to be crucial when we're trying to prove independence of things. So, contingency table shows how data frequencies are distributed for one variable contingent upon another. Contingent upon each level of the other variable. So in our example, if we're talking about the Titanic, obviously many of you seen the movie or heard it in history. Titanic, epic crash, big fail, 1917. We are 103 years past that. So in our example, we can examine the class of ticket contingent upon survival. This gives us a little more of a look as to see who lived and who died. Again, if we were in class, I would say, what do you notice about people in first class versus second class versus third class versus the crew? Who lived and who died? Also note that if we go all the way across, we have the frequency of number of passengers that lived and the number of passengers that died, or we have our row totals. And so we have each of these values that are total amounts in each of first, second, third, and the crew values. Those things are called something. We call those margins, where we have the totals, the marginal distributions. So the margins of the table, both on the right and on the bottom, give totals and the frequency distributions for each of the variables. The frequency distribution for each variable is called the marginal distribution because it resides on the margins. And this marginal distribution of its respective variable in the contingency table. So if we're looking for the marginal distribution of survival, we have 700 people that lived and 1490 that died. If we were looking for the marginal distribution of class, noting that we have both class as columns and survival as rows, we get our marginal distribution for class. With contingency tables, each cell of the table gives the count for a combination of two conditions. So for example, this second cell circled in the crew column tells us that 673 crew members died when the Titanic sunk. So we say that this 673 is both crew and dead. If we were using set notation, we would say crew upside down U and then died. With conditional distributions, a conditional distribution shows the distribution of one variable for just the individuals who satisfy a single condition on another variable. The following is the conditional distribution of ticket classes with the condition of having survived. So we could break out this entire row and say, let's just look at one of these conditions. Who lived? And what do we see from that condition for first class, second class, third class, and crew, knowing that our marginal distribution, or a relative distribution below with our percentages, is that we have 711 total people that lived or survived the Titanic. And then we see the breakdown of each. So the following is the conditional distribution of ticket class conditional on having perished. Notice that the first one was looking at ticket class condition on living. Second is the conditional distribution for ticket class conditioned on dying. If we were to compare these two different conditional distributions as a pie chart, it will tell us that there is a difference in the distribution of class for who survived and for those who perished. And you might be saying, okay, yeah, that seems pretty logical. So this is easily seen with pie charts of the two distributions. Note the obvious difference in section sizes between the two charts. And this leads us to a powerful conclusion, which we will investigate much later this school year. We see that the distribution of class for the survivors is different from that of non-survivors, which leads us to believe that class and survival are associated, and that they are not independent. Note, this also means if the relative distributions are about the same, then we do have independence, or there is no association. And that's what we want to measure with statistics. Are these related? What is the type of relationship? Or are they independent of each other? Does one affect the other? The variables would be considered independent when the distribution of categories of one variable in a contingency table is essentially the same for all categories of any other variables in the table. The last bit that we want to show in terms of displaying this information is we call things the segmented bar chart. So a segmented bar chart is, in essence, taking the same information from a pie chart and stacking it as a bar chart. Here is a segmented bar chart for ticket class by survival status. So we have alive and we have dead. Same exact information in terms of percentage that we had in our pie chart, just a better one-on-one comparison. Each bar is treated as the whole, so go up to 100%, which means that they have different amounts. We said that they were 711 people that lived and 1,490 people that died. So the total here is different, but we are now able to compare the percentages to see if there's some sort of association here. So each bar, therefore, is treated as the whole and is divided proportionally into segments corresponding to the percentage in each group. So this gives us our side-by-side comparison when we have these contingency tables or two-way tables, things that we want to compare. Each bar corresponds to a pie. The information portrayed is the same in each picture, but the emphasis is slightly different. So it really depends. What do you want to do with the data? And then what is the question that you're being asked here? So the last slide for this video is Simpsons Paradox. I bring this up. It sometimes shows up on the AP test, but it's kind of here and then it's gone. Simpsons Paradox is a result of averaging done when averages can be misleading. And this does lead us into trouble when we try to make conclusions when we don't have all of the context. So let's peek into the lives of two waiters in a local eatery. We're going to name them Gayad and Juchi. So here's the situation here. Gayad and Juchi are competing for a promotion to night manager. The restaurant manager decides to look at tip count to measure customer satisfaction. We have both of these surveys. We have both of these servers' performances for lunch and for dinner. And we see that Gayad served 50 meals and made $100 in tips at lunch and 100 meals with $600 in tips for dinner, versus Juchi sold 100 meals with $300 tip at lunch and 50 meals with $400 tip for dinner. Both come out to sell 150 meals with the same tip. So you're like, okay, what's the difference? If you just look at the marginal distribution of a waiter, it appears that Gayad and Juchi are equally well regarded by customers. But if we look a little closer, we go back to this and we look at each of those conditions for lunch and for dinner. Gayad averaged $2 per lunch she sold and $6 for dinner. And Juchi averaged $3 per lunch sold and $8 in tips for dinner. If you only look at these marginal distributions, you don't have context as to know who's doing what. But if you can break down the pieces a little more, it gives you more context. Averaging tips across lunch and dinner is unreasonable and is an example of Simpsons Paradox. This is another shout out. If you are able to get access to the Undoing Project, this is the type of work that Kahneman and Tversky talk about, which is what's detailed in the Undoing Project, which is the reason why I tied that book together with this course. So we're going to pause here. We have some words of caution to finish up this chapter, and then we are done with chapter 3, which will lead us to doing some practice problems with categorical data. See you, Falcons.